move ahead. Before I move ahead, let me try to do a question. Now, this question is a slightly difficult one. You don't need it. You don't need it unless you are aiming for the JEE mains and advanced. Okay. This is not there in your textbook. I am doing this primarily to illustrate the importance of maths. So here I have a bar of length L which has a charge Q uniformly distributed on it. I have a bar of length L which has a charge Q uniformly distributed over it. So can I say that the charge per unit length will become Q by L and it will be uniformly distributed? My question to you is, suppose from the midpoint I have a line. What is the electric field at this point P? Okay, so let me try to find out. So I take a small portion of that, and when I take a small portion of that, see, first thing is understand that the electric field is equal to KQ by R squared. Now what is this R? R is the distance of the charge from the point. Now you see this point is at this distance, this point here will be at some other distance. Cannot apply KQ by R squared. Why? Because R is not uniform. So whenever there is a point charge, you could apply KQ by R squared. Whenever there is a charge distribution, now you will have to start thinking. You can't apply KQ by R squared. So let's see how we can do it. So let this be equal to some small L. Now this is again, this is suppose some A. So this is root over of A squared plus L squared, Pythagoras theorem. Now the electric field here, assume this is all positive charge, it will push it like this. Now for this, I'm sure I will find another identical point which will push the electric field in this, which will have an electric field in this direction. So now if I take the y components, these two will cancel each other and the x component will remain. So can I say it will become 2 times E cos theta? Yeah. If this angle is theta. So if this angle is theta, this is going to be theta. This is also going to be theta because we said these two are identical points. Now what is E equal to? E is equal to 2 times lambda dl. This is having a small thickness dl. Lambda is the charge per unit length. So that divided by dl, divided by 4 pi epsilon naught r squared. R squared is A squared plus L squared. This is the 2 times E cos theta. Cos theta is going to be at this inside A divided by this. So it became 3 by 2. Now this is the small electric field because of this charge here. Now the total electric field will become integral of d. Total is nothing but the sum is nothing but the integral. So that will become integral 2 times lambda A dl divided by 4 pi epsilon naught A squared plus L squared power 3 by 2. Now you see, unless we know how to integrate this, there is no way we'll be able to move ahead. Now this is the context where you have to learn how to integrate certain standard functions. Okay, so I'll teach you how to do this and then we will move on. So I'll write down my question again. 2 times lambda A divided by 4 pi epsilon naught dl divided by root over of, not root over of, A squared plus L squared power 3 by 2. This is what we had. Yeah. Then the limits of the integral will, this side will be minus L by 2 and this side will be plus L by 2. But I have already taken 2 cos theta. So it won't be this. It will only be from 0 to L by 2. Right. So and where did it go? Okay, I'll write it again. So integral 0 to L by 2, 2 lambda A by 4 pi epsilon naught dl divided by A squared plus L squared power 3 upon 2. Now, if you see here, all these are constants, so they won't participate in the integral. So it is lambda a by 2 pi epsilon naught integral dl divided by a squared plus l squared part 3 by 2. The limits of the integral are 0 to l by 2. Yeah. Now, whenever you get an integral of this kind with a squared plus l squared, you make a substitution. Let L be equal to a tan theta. Let L be equal to, let's go back to our definition and see if this angle is there, tan theta will become equal to L by A. So L is equal to a tan theta. So here I have L is equal to a tan theta. So what is dl equal to a secant squared theta d theta. dl by d theta is equal to a secant squared theta. So dl is equal to a secant squared theta d theta. Then what will be this denominator equal to? It will become a squared plus a squared tan squared theta whole power 3 upon 2. So I can take a outside, it will become a cube 1 plus tan squared theta power 3 by 2. So 1 plus tan squared is secant squared. Secant squared theta power 3 by 2 will become secant cube theta. So now I can write this as lambda a by 2 pi epsilon naught integral dl is equal to a secant squared theta d theta divided by, in the denominator I'll have a cubed secant cube theta. Do you understand? This is what is known as integration by substitution. Whenever you have this form a squared plus l squared, this is the substitution that you do. Okay, this is standard. You'll have to memorize this. Now this is from 0 to L by 2. So now this will get cancelled here. It's also constant, so I'll bring it out. So I'll get lambda divided by 2 pi epsilon naught a. Secant squared will get cancelled. Secant will go up, will become integral cos theta d theta from 0 to L by 2. Now what is the integral of cos theta? Integral of cos theta is sin theta. So this will become lambda divided by 2 pi epsilon naught a sin theta. Sin theta. Now when I put my limits, it will become sine of 0 and the max L by 2. So it will become lambda by 2 pi epsilon naught a. Sin theta at maximum is L by 2 divided by root over of a squared plus L by 2 the whole square minus 0. So I have this. So this will give me the electric field at this point. Now I am asking you, friends, do you think this is an easy method or was it a difficult method? I found it difficult because it's very difficult to learn this maths. You all will agree? Now this is where Gauss's law made it very simple. Okay. Now suppose in this case, suppose that L was infinity. If L was infinity, this will be infinity, this will be infinity, so this will become 1. So the electric field will become lambda divided by 2 pi epsilon naught a. A is the distance from the wire, so I can say it is lambda divided by 2 pi epsilon naught r. Now you see how simple Gauss law is. Suppose I have a wire like this, and suppose this wire has a uniform charge density lambda. Okay, let me take a small Gaussian surface here. Now suppose this distance here is r. Now because it's an infinitely long wire, the electric field will be in this direction. Then the electric flux through this wall and this wall is 0. So if I apply Gauss law, integral E dot dA is equal to Q by epsilon naught is equal to lambda dl by epsilon naught. E goes out, dA is 2 pi r dl, the curved surface of the cylinder. If this length is dl, 2 pi r dl is equal to lambda dl by epsilon naught. So dl gets cancelled and I get electric field is equal to lambda divided by 2 pi epsilon naught r, which in our case would have become lambda divided by 2 pi epsilon naught a. Now, friends, which do you think is easy? Gauss law is far more easy, far more superior to Coulomb's law, because this makes life very easy for us. We are very easily able to find out. Okay, so this is where, or this is why we are trying to understand Gauss law. The only difference is here, this was a finite wire. Here, it's an infinite wire. Finite wire, we can't apply Gauss law, not because Gauss law is not applicable. Gauss law is a universal law. Gauss law is an universal law. It is always applicable. Gauss law is a universal law. It is always applicable. But we don't know the maths. Now, we don't know the maths to do it, because if it is finite, I can't assume that the electric field here will be in this direction, because the electric field will be sum of all these electric fields, right? And because it is not symmetric, the electric field will not be perpendicular to it. The electric field will have some component. Now, when the electric field has some component, we cannot apply. We can apply Gauss law even there, but we will not be able to bring E out of the integral. The moment we can't bring E out of the integral, the integration becomes difficult. So we are not able to apply. We are bound by maths. We are not bound by Gauss law. Gauss law is a universal law. We apply it to symmetric cases. We apply it to symmetric cases, those cases where it is infinitely long, so that the electric field can only be in this direction. Okay, so I hope this is understood. Yeah. Now you may ask, sir, why should we still do all those integrations? Well, you have to do integrations to learn how to apply maths. Okay, so you have to still do it. I have not done it, but as a JEE student, you have to do it. Same thing, I won't do it in a NEET class. It is not required. But in a JEE class, very essential. Okay, so here is a homework for you. This is a rod of, let's say, length 2L. Rod of length 2L. Somehow I am able to keep positive charge above the origin, and I am putting negative charge below the origin. I am putting positive charge above the origin. I am putting negative charge below the origin. My question to you is, at a distance A, what is the electric field? What is the electric field at a distance A from this system? Yeah. So here is my number. Now I'll start displaying the names of the students who have done the work and the names of the students who have not done the work. Again, I don't want a right answer. I just want an effort. So please make an effort and show me the effort. Yeah, the question is, what is the electric field at a distance A from the rod? Okay, so it should not take you more than half an hour maximum to be able to do this. Okay, let me work out one more question for you. Now I have a rim. A rim is like a ring. Then this is the axis of the ring. Okay, there's a problem. We'll sort it out.
Yes.
Vishnu, can you just?
Yeah, I make you host, sir. You can again start the screen.
Okay, done. Yeah. Yes, yes. So here is a question. There is a ring which has a charge Q uniformly distributed on it. The radius is R. So this is the relative of this question. There is a disk here of radius R which has a charge Q distributed on it. The question is, at this point, what is the electric field? Yeah, a charge Q is distributed on the disk of radius R. What is the electric field? At a distance A. So this is A from the center of the disk. Okay, so this is the question. So how do we go ahead with it? Okay, so the way we go ahead with it is this. So see, this is, I'm taking again, the charge is uniformly distributed. So again, KQ by R squared won't work. KQ by R squared won't work. I don't know what Q to take. I don't know what R to take, because R can be from here, from here, from here. It can be from anywhere. So what I do is I try to now divide the disk into small strips. Okay, small strips. Now, if I take this particular strip here, this will have an electric field in this direction. If I take this one here, this will also have an electric field in the same direction. So the net field will be the cos component of that. If this angle here is theta, it will be the cos component of that. And of course, this is a ring. So that is the homework that I have given you. So a disk can be considered to be having many rings. So if Q is the total charge, so the charge density will be Q by pi R squared. Now here we are talking of a surface charge density. We are talking about a surface charge density. So Q divided by pi R squared. Again, let me just warn you, this is not required for your NCRT. You will never get these kinds of questions. Even in your notebook, you may make a note of it. We are doing these questions purely to understand Coulomb's law better. Okay, and to understand the applications of mathematics. There will never be a question of this kind in your board exam. This is required for all those of you who want to improve your ability to think. This is required for all those of you who are aspiring to get into a NIT or an IIT. Okay, so this is at a slightly advanced level. This is purely for you to understand applications of maths. If you're finding it difficult, just ignore it. We'll do the easy thing in few minutes. So Q divided by pi R squared is the surface charge density, right? Now, suppose this charge here is some dq, then can I say that the electric field there here is, this radius be equal to R. So it will become equal to K dq divided by, I want to take cos theta, cos theta will be 3 by 2 again, and another A here. Yeah. Now, when I want to find out this dq, what is this dq equal to? dq will be q divided by pi R squared into a dr and some dl into dl. See, the dq will be one small strip like this. This side it will be dr and this side it will be dl. Now I have to find out the integral over dl, that is over the entire ring. So entire ring R is a constant, so there's no change there. So the integral is very simple. dq will become equal to charge density pi R squared into the area of this ring. What is the area of this ring? 2 pi R dr. Yeah. So when I now work it out, the electric field at this point because of this ring is equal to K. This is Q. This is A, 2 pi R. So A into 2 pi R dr divided by pi R squared into r squared plus a squared power 3 by 2. Now you have to integrate this to get the value of the total electric field there. Now the integral will be from 0 to r. In the previous example, I taught you how to do dr by r squared plus a squared power 3a by 2. Now there is a r here. So now again the way you integrate is going to change. So let me simplify this a little bit and then again do this. So pi will get cancelled. So then kqa, so 2kqa, so it is 2kqa. So 2kqa r dr. 2kqa r dr divided by r squared plus a squared power 3 by 2, where a is the distance from the disk, r is the radius of the disk. The small r is that variable r. So now you're going to integrate this from 0 to r to be able to get this, right? Now how do we do? See, the difference between earlier and here is the presence of r. So now here we do the substitution. Let r squared plus a squared be equal to some t squared. So if I differentiate this, I'll get 2r dr is equal to 2t dt. 2r dr is equal to 2t dt. Let me substitute that and then check. So I have a 2r dr. So it becomes integral 0 to r kqa 2t dt divided by r squared. This will become t cubed. Now t and this will get cancelled to become t squared. Now, do you know integral of t power minus 2 dt? Integral of t power minus 2 dt is what? T power minus 2 plus 1 divided by minus 2 plus 1. Integral of x power n dx is equal to x power n plus 1 by n plus 1. So I have to apply the same thing here. So this will become equal to t power minus 1 by minus 1. So when I supply this here, it will become kqa, kqa, 2t is gone, but okay, 2kqa, then again minus by r squared 1 by t, 0 to r, but r squared plus a squared, you will understand this. R squared plus a squared is equal to t squared. So the other limit of t will be root over of this much. So when I substitute, it will become minus. So it will become minus 2kqa by r squared 1 by root over of r squared plus a squared minus 1 by a squared. So I can take the minus inside. It becomes 2kqa by r squared 1 by a squared minus 1 by root over of r squared plus a squared. Sorry, this is not a squared, 1 by a minus this much. Okay, so this is what it will be. Suppose the r value is large, like this is an infinitely long disk. If it's an infinitely long disk, then what it is? So we will see. But I hope you are able to understand this much. Okay, so if it's an infinitely long disk, this will become 0 to find out limit a tending to infinity, not a, r tending to infinity. This q by r squared will become charge density. So 2 by 4 pi epsilon naught. Q by 2 by 4 pi epsilon naught. Q by r squared into a into 1 upon a. This will become 0. So the a will get cancelled. 4 pi r squared is area. Q by area is charge density. 2 will get cancelled. So it becomes sigma by 2 epsilon naught. Now we have used Coulomb's law to get this. Now I will do the same thing by using Gauss law. Suppose I have a plate which is infinitely long. This is the surface charge density. Okay, now the question is, what is the electric field near the plate? So the way you go ahead is, see, the plate will have a charge on both the sides. So there will be an electric field going this side, there will be an electric field going this side. Now on the side walls, the area vectors are perpendicular. So there is no flux here, there is no flux here. So flux is there only on this shaded portion and on this shaded portion, and this is where the charge is. So this will be E into A. This will give you another E into A. This must be equal to Q by epsilon naught. Q here is nothing but the charge density sigma into A by epsilon naught. So 2 times E into A is equal to sigma into A by epsilon naught. So the area get cancelled. So the electric field is equal to sigma by 2 epsilon naught. See, what we took so much time to do while we were working with the disk and Coulomb's law, we could do it in a fraction of a minute by using Gauss law. So if you apply Gauss law, the electric field is equal to sigma by 2 epsilon naught. I will do it again. You make a note. First you make a note, you understand this again properly. Again, and then you go to the next one. I'll explain it again. Okay. So this is not required for all of you. Only those of you who are serious that yes, I have to do it. I have to get into the IIT. I have to get into the NEET. Please work it out. So here I wrote the question and then I provided a solution for it. So here is this integral. So I told you now that whenever we have an integral of this kind, this is a substitution. With R, you make this substitution. If this R is not there, then tan theta substitution. This is what we will call it as integration by substitution. Okay. So you are primarily learning how to apply maths to physics. That is very, very important. You have to understand that this charge is not a point charge. Only for point charge, we can say the electric field is kq by r squared. For all other charge distributions, we will have to think and then work. Okay. Now, if you understand that, so let me tell you how to go ahead with it. So I'll explain here. Suppose you have a plane. Suppose this plane has a uniform surface charge density sigma. For points close to it, how do I find out the electric field? Then here is where the charge is. So in this cylindrical Gaussian surface, the electric field goes this side. So the flux on the side walls is 0. Why? Because the electric field and the area vectors are perpendicular. So flux only is there here and flux is only there here. So suppose this area is A and the electric field here is E. So E into A plus E into A. One E into A on this side, one E into A onto this side. So this is equal to Q by epsilon naught. Q is sigma into A by epsilon naught. So 2 times E into A is equal to sigma into A by epsilon naught. So the area get cancelled and you get that the electric field is equal to sigma by 2 epsilon naught. Okay, so exam, sometimes it also comes as a 3-mark question. The question is, what is the electric field between near a infinitely charged plate? Again, why should it be infinitely charged plate? Only for an infinitely charged plate will the electric field be perpendicular to the surface. If it is not infinitely charged plate, it will be at some angle. Again, we will be finding it difficult to work. Okay, remember Gauss law is not a limiting law. Gauss law doesn't have any limitations. Gauss law is universally applicable. But we want that maths to be easy. We want that integral E dot dA, we want this E to be constant. So if E is constant at all points, we can take it out of the integral. To make integration easy, we don't want to do all this and then give an answer. So to make it easy, we are working it out this way. Okay, it's very important for you to understand the spirit of Gauss law. Okay, so this is a surface charge density. Surface charge density is also referred to as a superficial charge density. So some of you might be thinking that, look, this is not dimensionally correct. This doesn't look dimensionally correct because electric field is 1 upon r squared. There is no rd here. But understand, charge density is what? Q by area. So area will have an r squared and dimensionally it will be perfectly correct. So if I can recollect for you, you have seen a point charge. For a point charge, electric field is proportional to 1 upon r squared. Then you have a dipole for which the electric field is proportional to 1 upon r cubed. Then you have a line charge where the electric field is proportional to 1 upon r. Then now you are having a plane where the electric field is independent of r. Independent of r. Next, I will show you a place where it is proportional to r. So let's go to the next situation. The next situation is the electric field. Suppose I have a conductor and I have given it a uniform charge distribution. If I have a conductor and I have given it a uniform charge distribution, in the last class I explained to you that in this case, if I consider a Gaussian surface here, one, charge is static. Charge is static. Static means we are assuming that it is uniformly distributed, right? Charge is static. Second thing is it's a conductor. What is a conductor? Conductor will allow charge to move. A conductor will allow charge to move, right? So if a conductor will allow charge to move, then, and we are saying that it is a static condition, let's see what happens. So if I apply Gauss law, integral E dot dA is equal to Q by epsilon naught. So E into 4 pi r squared is equal to Q by epsilon naught. So E is equal to Q by 4 pi epsilon naught into r squared. Right? That means there is some electric field at this point. If there is an electric field, there will be a force acting on the charge which is there. And so this is not possible. So this, whatever we are saying, is not possible. That means what? The net field here must be 0. Only then the charge will not move. So if the net field here is 0, what should be the total charge inside? 0. That means all the charge is inside. So inside the conductor, there cannot be an electric field. That's what I was trying to explain to you the other day. A Gaussian surface like this, the net field here is 0. So if I take a conductor, once I cross the surface, E electric field is proportional to this side is R. So electric field is proportional to 1 upon R squared. So I explained this to you in the last class, right? Now let's see what if it is not a conductor, but if it's an insulator. So here I have, so now I have an insulator. How is an insulator different from a conductor? An insulator will not allow the charges to move. Yeah, so the charges will remain wherever they are. So if the charges remain wherever they are, now the question is what is the electric field at some point? So I am drawing a Gaussian surface. So now I am going to apply Gauss law here. So integral E dot dA is equal to Q by epsilon. Where what is Q? Q is the total charge which is present inside. So Q is the total charge present inside. So if Q is the total charge present inside, can I say E into dA, integral dA is equal to Q. Suppose the charge density is rho into 4 by 3 pi r cubed by epsilon naught. Yeah, what is dA equal to? dA is equal to 4 pi r squared. So This 4 pi here will get cancelled. This r squared here and will get cancelled. So I'll get rho into r by 3 epsilon naught is equal to E. Now there is an electric field. Now because this is an insulator will not allow the charge to move. So now this is the electric field. Now if I draw my graph here between the r value and the electric field value, this goes a straight line. Why? Because E is proportional to r. Then once you reach the surface, once you cross the surface, there's an inverse proportionality. So it goes this way. So here it is again proportional to 1 upon r squared. Yeah. So I hope you are able to understand this. This is a very important 3-mark question. 3-mark question along with this graph. Along with this graph, the question is what is the electric field inside and outside a insulator which has a uniform charge distribution. So I have a uniform charge distribution. What is the electric field inside and outside? Okay, so I hope you are able to make a note of this. If you are able to make, I just stop for a minute and then I will move ahead. So please make a note. Okay, now if you understand this, then let me try to work it out for you again. Let me explain some small things to you again. First, we took an infinitely long wire and I took a Gaussian surface, the cylindrical Gaussian surface, and I applied Gauss law here, and then we got lambda L by epsilon naught is equal to E into 2 pi r L. The L get cancels and I get E is equal to lambda divided by 2 pi epsilon naught r. This one I hope you are understanding. In the second one, I took a plane. Then I drew a Gaussian surface inside and outside the plane. This is inside the plane. This is the charge where charges. So the electric field goes this way and this way. So I said on these walls, the flux is 0. Only on these plane walls will there be a flux. So I said 2 times E into A is equal to Q by epsilon naught. That Q is sigma into A by epsilon naught. So the A get cancelled and I got E is equal to sigma by 2 epsilon naught, right? So this is the electric field near an infinitely long plate. Here the point to understand is the electric field is independent of D. Next I took a case of a conductor, giving it a uniform charge. Then we said, look, in a conductor of uniform charge, all the charge will come to the surface. So the electric field will not be there till you reach the surface. Once you reach the surface, electric field will become 1 upon r squared. Then I took an insulated sphere. In an insulated sphere, I gave it a uniform charge density. Now again, E into integral dA will give me Q by epsilon naught. So he into 4 pi r squared is equal to rho into 4 by 3 pi r cubed by epsilon naught. So this r squared, r cubed got cancelled, 4 pi got cancelled, and I got E is equal to rho r by 3 epsilon naught. Okay, this is inside. The moment I go outside, it will again become like it goes straight this way and then comes this way. So this is R here, this is E here. Okay, so this is how it changes. These 4 questions are very, 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 very important. In every exam, you will get 1 or 2, not 2, one question of this every exam you will get. If there are 5 papers in your board examination, every examination will have a question of this kind. What is Gauss law? And with the help of Gauss law, find the electric field here or here or here or here. Okay, so this is very, 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 very important for you. Please make sure that you are able to understand this. Yeah, you please practice on it once or twice. We will make all these videos available so you can listen to them once or twice. Understand that the 11th physics is little bit more practical than the 12th physics. So 12th physics is a little difficult. It is not theoretical. Only when you work on it again and again, it will come. Otherwise, it doesn't come. But 12th physics is very easy to master. If you master 12th physics, definitely whichever entrance you are aiming at, you will be able to crack the entrance. Okay, so this is what it is. Yeah. Next, we have few small, very small things to do. One is we need to talk about dipoles a little bit more. So we have not spoken much about dipoles. So I will speak a little bit about dipoles. If I speak about dipoles, I think we have finished this chapter. Now for the next at least 2 classes or 3 classes, we'll only do numericals so that we will be able to understand. Now, I hope and request all of you to please work out and answer and try to answer the book back questions, try to form answers for the book back questions. Please send me your response to this number so that I can go through it and tell you whether you're doing it right or wrong. So it is important that you start working. Yeah. So little bit dipole I'll do today, but next class we'll do dipoles. With that, we'll be finishing it off. And then we will only look at numericals. See, I'm going to now place a dipole in an external field and then see what happens. See, this is basically first, what is a dipole? A dipole is two equal and opposite charges separated by a distance. Equal and opposite charges separated by a distance. Suppose this distance here is L, this is plus Q here, this is minus Q here. Yeah. Now, first thing is you may also ask how are dipoles created. Don't worry, let's start from there. How are dipoles created? Now here I have a dielectric material. I have a dielectric material. Dielectric is nothing but an insulator, mica. Insulator. Plastic, mica, paper, all these are dielectrics. Let the dielectric constant of this be equal to K. Now I put it in an external field. I put it in an external field. First thing is, if E is the electric field outside, what is the electric field inside? We have already learned from Coulomb's law. It will simply be equal to E divided by K, right? So let us see what happens. See, an insulator is made up of some nucleus, and there are some electrons which are rotating around it. Yeah. Now, when I put an electric, this is the typical case. The positive center and the negative center are the same. Now, when I put an electric field, what happens is the positives get to one side and then it like this happens. This happens. So when this happens, the negative center has come here. The positive center is here. The negative center is here. So if the negative center is here, equal and opposite charges separated by a distance. So this is a dipole. This is what we refer to as polarization. So polarization may take place and dipoles may be generated. On the other hand, you have simple water molecules, O, H, H. This oxygen is more electronegative, so it pulls the shared pairs towards itself. So it gets a negative charge, hydrogen gets a positive charge. Again, equal and opposite charges created, separated by a distance. So dipoles are generated either this way or this way. Okay, so now let's go to this case. It's pretty interesting. Now you see the positives, there seem to be some positives on this side and there seem to be some negatives on this side. Now, if this is the case, do you see that there will be an electric field in this direction? So you have an electric field, external field, minus you have an electric field due to polarization. See, the electric field due to polarization is opposite to the external field. And this gives you the net field. What is the net field equal to? Net field is equal to E divided by K. So can I say that the electric field due to polarization is E into 1 minus 1 by K? This is the electric field only due to polarization. Now, if this is a situation, we already know, suppose it was a conductor, K is infinity. So if K is infinity, this becomes 0. That means the charge due to polarization is E. So the net field is equal to 0. But for any other insulator, if you keep an insulator in an external field, if you keep an insulator in an external field, polarization takes place. Polarization consumes energy, and that electric field due to polarization is E into 1 minus 1 by K. The net electric field is equal to E by K. This was a question which came in the JEE mains. This was a question which came in the JEE mains. Yeah, so we need to, this is the logic for this. Yeah, try to think about it, try to read, try to write notes. Only when you write more, you will learn more. Okay, so what I'll do is I will stop here today. Next class, what I'll do is I'll talk only about dipoles. You've already seen a little bit about dipoles, but I'll talk about dipoles and we will do dipoles in detail. Next class, tomorrow's class, we'll work only with dipoles. So today, what did I do? I spoke about this line charge. So you may have a look at it. We applied Coulomb's law on line charge, and then we saw how difficult it was to find the electric field. So I got this, then I got this to show you. Then I taught you how to do this integral by taking integration by substitution. And then we got this, and then we finally got lambda by 2 pi epsilon naught a by taking limit L tending to infinity. Next, I applied Gauss law and I did the same thing and showed you, look how simple Gauss law is. That is the beauty of Gauss law. If we don't apply Gauss law, it takes us so much time and energy. But if you understand what is Gauss law, we do it in a few minutes. Then I explained to you about the concept of symmetry and the fact that Gauss law is universally applicable, just that we are not applying it to all those cases where the maths becomes a little difficult. We are not applying it there. So that is what I said, symmetric cases. Symmetric cases mean all those infinite cases. Then we did this, I told you this, we did the symmetric cases. I gave you a homework. If I have a line charge, up positive, down negative, I asked you what is the electric field on the axis. Then I gave you my number and I told you please message it. Then I also told you that last time only some 10 of you have submitted your answers, others have not. Please try to work it out. It's not about getting the right answer. It is about applying your mind to get it. There is a lot of resistance. The mind has a lot of resistance. Memorize it and go. But if you want to achieve something, you have to force yourself to work. Then I gave you another question also. I gave you a ring and I told you to find out the electric field due to a charged ring. So I gave you a ring like this. I told you to, this ring has a charge Q, it has an area A or R. I asked you to find out at a distance A, I asked you to find out what is the electric field. Then I said, I'm going to do a more difficult question for you. And I took a charge Q uniformly distributed on a disk of radius R. And I asked you what is the electric field at a distance A from the center. So I applied, first I explained to you why Coulomb's law cannot be applied, because here the R values are not the same. So in all cases of charge distribution, you cannot apply Coulomb's law as it is. Then I showed you this. Then I did this for you. I found out, I applied Coulomb's law for the dq and I explained to you how to do the integral. If you have not understood it, don't worry. I will explain it again in the next class. Then I took an infinite plane and then I found out using Coulomb's law and I explained to you how easily it can be done. Then we took a volume charge distribution, explained it for a conductor. Then we took a volume charge distribution, explained it for an insulator. Then I summarized the whole thing. And I said tomorrow we will talk about dipoles. Okay. So thank you. You all should be reading a lot. This is not very easy. At the same time, this is not very difficult. So you need to work. If you work, you will be able to get it. Okay. So thanks. Enjoy working and use your time productively. Bye.